This meeting is being recorded.
In section 3.4, we're now going to look at how we can qualify acidity. Not so much quantify it with a numeric value, but just look at the stability of a resultant conjugate base after an acid loses a proton to determine the strength of the acid. So that's going to be our technique, and we're going to look at different ways of figuring this out. So in general, you should note the stronger the acid, so this bullet point here, right, the stronger the acid, the more stable its conjugate base. And when this acid loses a proton to form the conjugate base, we're actually going to look at this lone pair of electrons and the stability of that lone pair. So that's the specifics of how we're going to determine qualitatively acid strength. So there are multiple ways. So we're going to use this memory device here, this ARIO acronym, to help us remember what to look for. So the first of these four factors, the A, would be the type of atom that carries a charge. So we're going to compare electronegativities, and the more electronegative atom will be more stable with a negative charge, and the opposite will be true. The least electronegative atom, if that has a positive charge, things of that nature. So we'll look at atom that carries a charge. We'll look at resonance. Is there a resonance form possible? Because we know that resonance adds stability. Is there induction? So we'll look at things like electron withdrawing groups. So again, very electronegative atoms tend to withdraw electrons from bonds or from other atoms. And then last but not least, we'll look at what type of orbital has this charge. So things like the orbitals sp, sp2, or sp3 will determine stability. So using this acronym, let's take a look at our first category here, the A. So the type of atom that carries the charge. So let's compare our two acids below here. So butane, this hydrogen can be acidic in certain conditions, and propanol we see in OH, so this is an alcohol, but its hydrogen can also be acidic under certain conditions. So let's draw the conjugate base that results, and this will be after we remove a proton. So here we see our butane without a proton, so there's a negative charge on a carbon. And then over here, we have propanol has lost that proton, so now we have a negative charge on our oxygen atom. So we kind of consider which of these two conjugate bases would be able to be more stable. And that has to do with which atom holds the charge. So carbon is less electronegative than oxygen. They are in the same period as we see down here. So it goes, carbon, and then oxygen is even closer. Well, there's nitrogen in between, of course. So carbon, nitrogen, oxygen, and then we have our most electronegative atom, fluorine. So oxygen will be able to stabilize a negative charge much easier than our carbon. And also, if we look at going down a column, the larger the atom, so as you go down, the larger, the easier it is to stabilize a negative charge as well. So if we had to compare, say, oxygen to sulfur, sulfur would be a little bit better than oxygen. So in this case, then, we see that the alcohol, it has the more stable conjugate base, so therefore that would be a stronger acid than our alkane. So let's look at this one more time and put it all together. So the relative stability of these conjugate bases tells us the relative strength then of the acid which the conjugate base came from. So We have butane is less acidic because its conjugate base is less stable. Propanol, more acidic because its conjugate base would be more stable. So let's look at the second factor that can help us determine stability, or rather qualify our acidity. Resonance. Resonance can stabilize a negative charge by spreading it out over multiple atoms. So let's compare the acidity of an alcohol, and this guy over here is acetic acid. So you may not be surprised what the outcome is based on the name. So let's take a look. Which of these species has resonance? So we see the deprotonated alcohol over here, this ethanol, ethoxide that results, and this does not have resonance to stabilize that negative charge. So this would be overall less acidic, but our carboxylic acid, our acetic acid over here, you can see these two resonance forms. Therefore, our charge is delocalized from one atom, so it's spread across multiple atoms, and therefore this would make acetic acid a more acidic compound. And then, of course, we can confirm quantitatively by looking up pKa values. So now we look at this factor of induction. So this can also stabilize a formal negative charge by spreading it out. But let's look at how induction is different than resonance. So now we focus on these electron withdrawing atoms or groups. So we're looking for a very electronegative atom compared to a less electronegative atom. And these electronegative atoms, so we have chlorine here. These are right next to fluorine, right below fluorine. So these are all good electron withdrawing groups. So these can stabilize that negative charge through induction by grabbing electrons or pulling electrons towards them. So again, we're comparing acids to acids here, and acetic acid, even though it's called an acid, will be less acidic than trichloroacetic acid, which is the same structure, but instead of hydrogens, we have these 3 chlorine atoms. So because of these electron withdrawing groups, through induction, trichloroacetic acid will be more acidic, and this proton here will be much easier to remove than this proton here on acetic acid. So let's look at some of these pKa values and see if we can see this trend now through induction. So more electron withdrawing groups will give us a more stable conjugate base. So that's the take-home note from the slide here. So we have our acetic acid, no electron withdrawing groups, 1 electron withdrawing group, 2, and then we have those trichloro form of our acetic acid here. And notice the pKa is the lowest. It's below 1 at this point. So this is now a fairly strong acid. The closer the electron withdrawing groups are to a negative charge, the more stable the conjugate base will be as well. So if we had a larger structure here, so say we extended this acetic acid a couple carbons longer, and we put some chlorines down here and form this trichloro acid, because the electron withdrawing groups are further away from all this negative charge here, the inductive effects will be less. So the closer the electron withdrawing groups, the more stable, and the more electron withdrawing groups, the more stable the conjugate base. So let's look at our last consideration here. So we have the O in aereo, so the type of orbital. So as you see over here, we have 3 types of hybridized orbitals. We have sp3, sp2, and sp. So now notice the sp is the smallest orbital. the closer electrons are held to a nucleus, so the closer they are to the nucleus, the more stable they are. So that means these smaller hybridized orbitals are shorter, sp specifically, so therefore they would be able to stabilize a charge, a formal negative charge, better than, say, an sp3 hybridized atom. So sp hybridized orbitals are more stable in this case than we have sp3. So again, the type of orbital tells us which proton would, if it were removed, which would form the more stable conjugate base. So if we removed this proton over here in red, this would result in a carbanion here that is sp2 hybridized. And over here, we see if this proton in blue was removed, this will be an sp hybridized carbanion. So the lone pair is in an sp orbital, so therefore it's held closer to the positive charge of a nucleus, and this one will be more stable over here. So again, the less acidic proton would create a less stable conjugate base, and it will be in a longer orbital that's further away. And then we have the more acidic proton that's determined because it will be in an sp orbital and then more stable. So the last few slides in this section, actually there's quite a few, so we'll keep going here. Let's look at some more orbital practice. So if you recall, we can look at this carbon here, and we can see that all of these bonds would be sp3 hybridized between the 3 hydrogens and then to the other carbon. Here we would have just sp2 hybridization of ethylene, and then right, this proton, this carbon, right, this is just sp hybridized rather on this carbon here. So this would be the most acidic, this 2-carbon structure, this acetylene, because of its sp hybridized orbitals. And then the weakest acid that would result will be ethane with a pKa of 50. So we can see how our orbital consideration and then our actual pKa values correlate. So again, we can use Ario as our guide to assess all of these stabilizing effects. And of course, there are some exceptions. So let's take a look here. We have our ethanol, we have propylene. So ethanol is more acidic than propylene, so the conjugate base of ethanol must be more stable. So that's what we can see over here. So the type of atom would be what our consideration is here, the type of atom, which one is more electronegative. So oxygen here can hold or can stabilize that negative charge because it's more electronegative than can a carbon. And also we can note that propylene's conjugate base can be resonance stabilized, which could suggest that it's more stable. But in this case, we actually see that ethanol is more stable. But if we prioritize atom before resonance, so the order that we see ARIO is the order that we should make these considerations. So the atom wins here over the resonance stabilization. So there are some times when Ario fails. You should not experience this. Maybe in a homework problem you might see when this fails as our guideline, but generally you can follow Ario and get the correct answer every time. So what we see here is that the equilibrium would lie to the left based on our stability of charge. We would think that that nitrogen will be able to hold that charge, that -1 formal charge, better than carbon, but we would be wrong. So this is actually based on pKa values, the stronger acid. Our ammonia here is a weaker acid, so we actually find the equilibrium will lie in this direction, towards the right. So sometimes you just need to know pKa values to make the correct assessment. So see if you are able to predict the red versus the blue protons in these scenarios here. So let's look at A. If we were to remove this proton here, we would end up with a lone charge on our carbon. If we were to remove the red proton here, we would end up with an extra lone pair on this oxygen. So based on what we just looked at, if we remove the red proton, we would see a much more stable resonance structure, a much more stable conjugate base, and oxygen is just in general able to hold that negative charge better because it's more electronegative than a carbon atom. So the red hydrogen wins here as far as being more acidic. So see if you can figure out with B and C which would win, which would be the more acidic proton. And we will continue with actually with section 3.6 next time. There's not much from 3.5 in the textbook, and we will not cover PowerPoint slides on section 3.5.